Baseline classifier. In order to fix a baseline, to be conscious about whether we are developing useful models or not, a baseline classifier is required. A baseline classifier always predicts the majority class, and it is the simplest classifier we can build. The majority class represents a 23% of the whole dataset. For that reason, that would be the accuracy of a majority class classifier. Now, if you're wondering how we arrived at the 23%, if you remember the graph we saw in the previous few video lectures, it suggested to us that among the five different categories of the news, the sports category has the highest number of articles, which is 23%. We now have the random forest classifier. The random forest, like its name implies, consists of a large number of individual decision trees that operate as an ensemble. Each individual tree in the random forest spits out a class prediction, and the class with the most votes become our model's prediction. The fundamental concept behind random forest is a simple but a powerful one. That is the wisdom of crowds. In data science, in the language of machine learning or data science, the reason that a random forest model works well is that a large number of relatively uncorrelated models, that is, trees, operate as a committee and will outperform any of the individual constituent models. The low correlation between models is the key. Just like how investments with low correlation, such as stocks and bonds, come together to form a portfolio that is the greatest, that is greater than the sum of its individual parts, uncorrelated models can produce ensemble predictions that are more accurate than any of the individual predictions. The reason for this wonderful effect is that the trees protect each other from their individual errors. As long as they don't constantly have error at the same time. That is, not to make sure that none of the individual trees have the same error at the same time. While some trees may be wrong, many other trees will be right. So, as the group, the trees are able to move in the correct direction. So, the prerequisites for a random forest to perform well are: the first one would be that there needs to be some actual signal in our features so that the models built using these features can do better than random guessing. The predictions and therefore the errors made by the individual trees need to have low correlations with each other. Now looking at how we perform random forest classification, we import all the necessary packages and libraries as we have done in most of our way so far. Then we load the data, we check the dimensions of our feature vectors, and then we perform cross validation for the hyperparameter tuning as we had discussed earlier. First we see the what hyperparameters the model currently has. So we have these hyperparameters such as bootstrap, class weight, criterion, max depth, max features, max leaf nodes, minimum impurity decrease, and so on. We will tune the following ones. There are there are 17 parameters currently in use, but out of these 17, we will be tuning 6 parameters, namely the n estimators, that is the number of trees in the forest, the max features, that is the max number of features considered for splitting a node, the max depth, that is the maximum number of levels in each decision tree, minimal or minimum sample split, which is the minimum number of data points placed in a node before the node is split, minimum samples leaf, that is the minimum number of data points allowed in a leaf node, bootstrap, which is a method for sampling data points with or without replacement. Then we perform the randomized search cross-validation. To perform this, we first need to define the grid. So for n estimators, we start the grid at 200 and stop the grid at 1000, and the number of grids would be 5. So it can be noticed that since the number of grids would be 5 and uh, the grids would be at every interval of 200, that is at the starting 200, of 400, 600, 800, and the ending, the last one, that is 1000. Similarly, we will perform the grids randomized search cross validation for features like max features, maximum depth, minimum samples split, minimum samples leaf, bootstrap, and so on. We will then perform the random search. Putting 3 folds for each of the 50 candidates, totaling 150 fits. We can see the best hyperparameters resulting from the random search are as follows. Best hyperparameters from random search are the n estimators 800. Remember how we had the grids at 200, 400, 600, 800, and 1000 for n estimators? The best hyperparameter was found to be when n estimators was at 800, and the minimum samples split was at 10, minimal samples leaf was at 1, max features was square root, max depth was 40, and bootstrap value was false. The mean accuracy of a model with these hyperparameters was found to be 94%. After that, we could do more exhaustive search centered in those values. Fitting 3 folds for 27 candidates here in this scenario instead of the earlier tested out model for 50 candidates, hence totaling 81 fits. For this, we found that the accuracy was 94.5%, but for the 50 candidates, we found that the accuracy was 94.23%, which shows that this tuning performed better results. By similarly changing the parameters slightly, we can try to find the best results, best possible results. But when the candidates were 27, we found that it formed the best possible result. Model fit and performance. Now we can fit the model to our training data and get the predictions. The conditional class probabilities can be obtained by typing RFC pred, short for prediction, RFC being random forest classifier, and best random forest classifier dot predict probability feature test. For performance analysis, we will be using the confusion matrix, the classification report, and the accuracy on both training and the test data. The training accuracy was found to be 1, the test accuracy was found to be 92.8%. When I when we say that the training accuracy is 1, we usually mean 100%, but it can also be called as 1. We see that the test accuracy is lower than the training accuracy because the testing works on unseen data. Finding the classification report, we have the precisions as follows: in the 87%, 90%, 97%, 97%, and 95%. And similarly, we have different values for the recall, F1 score, and support. Averaging it out, we get the precision as 93%, recall as 93%, F1 score as 93%, and the support value of 334. You can now see the confusion matrix where different values are found. For business, it's 77. For entertainment, it's 46. For politics, it's 62. For sports, it's 69. And for technology, it's 56. At this point, we could get the average time the model takes to get predictions. We want the algorithm to be best, to be the fastest and the best, since we are creating a model which performs best with respect to the baseline classifier. We've now formed the table where we have the training set accuracy as 100% and test set accuracy as mentioned above, it's 92.8%.